Section 1. What's a hydrocarbon? Let's break it down. Have you ever wondered what makes up the world around you? It's all about chemistry. And one of the biggest families in chemistry is the hydrocarbon family. Consider the name, hydro and carbon. That's it. These are molecules made of just two things, hydrogen atoms and carbon atoms. They are the simplest organic compounds, but they are incredibly important. Carbon is amazing because it loves to connect with other atoms, forming long chains or intricate structures. It's like the ultimate building block for molecules, creating the backbone for so many substances we use every single day in our lives. Think about the fuel in a car. That's a hydrocarbon. The natural gas that might heat your home or cook your food? That's methane, another hydrocarbon. These molecules are packed with energy. When we burn them, the bonds between the carbon and hydrogen atoms break apart. This releases a whole lot of energy in the form of heat and light. It's this energy release that powers our cars, heats our homes, and runs our factories. So, these simple combinations of hydrogen and carbon are literally fueling our modern world. They are the power source hidden in plain sight, a fundamental part of our energy system. Hydrocarbons can come in all sorts of shapes and sizes. Some are very simple, like methane, which has just one carbon atom and 4 hydrogen atoms. Others are much more complex, forming long, winding chains. Imagine a long chain of paper clips, where each paper clip is a carbon atom, and little bits of tape on the sides are hydrogen atoms. You can have short chains, long chains, and even branched chains. This variety in structure is what gives different hydrocarbons their unique properties, making some good for fuel, and others better for making plastics or other materials. So, to put it all together, hydrocarbons are the foundation of organic chemistry. They are molecules made exclusively of hydrogen and carbon atoms, bonded together in various ways. They can be straight chains, branched chains, or even form rings, which we'll get to in a moment. From the gasoline that gets you from place to the wax in a candle, these simple-sounding molecules are everywhere. Understanding them is the first step to understanding a huge part of the chemical world we live in. It's science, and it's all around us. Section 2. Meet the Aromatics, the special ring club. Now let's get to a really cool group within the hydrocarbon family. They are called the aromatic hydrocarbons. Why aromatic? Well, the first ones that scientists discovered had very distinct, often pleasant smells. Think about the sweet scent of wintergreen or the smell of vanilla. Those smells come from molecules that belong to this special club. So, the name stuck. Even though many aromatic compounds don't have a strong smell at all, it's a name from history, but it points to a very unique chemical structure that sets them apart from the straight-chain hydrocarbons we just talked about. What makes an aromatic hydrocarbon so special? It's all about their shape. Instead of long chains, these molecules form a flat ring. But it's not just any ring. It's a ring with a special kind of bonding that makes it incredibly stable. Imagine a group of friends holding hands in a circle. They are all connected, making the circle very strong and hard to break. Aromatic hydrocarbons have a ring of carbon atoms that share their electrons in a very special way, almost like they are all holding hands together in a super strong loop. This unique arrangement is the key to their identity. This special electron sharing is called delocalization. That's a big science word, but the idea is simple. In a normal chemical bond, 2 electrons are shared between just 2 atoms. But in an aromatic ring, some of the electrons aren't stuck between 2 atoms. Instead, they are free to move all the way around the entire ring. It's like a racetrack, where the electrons are the cars, constantly zooming around the circular track. This movement spreads the energy out and makes the whole molecule extra stable and less likely to react than other hydrocarbons. So while all hydrocarbons are made of hydrogen and carbon, aromatics are the VIPs with a secret. They have a flat ring structure and a unique system of shared, delocalized electrons that gives them special properties. This stability is their superpower. It means they behave differently in chemical reactions and can be used to build other, more complex molecules. They are not just your average hydrocarbon, they are members of an exclusive chemical club, defined by their structure, their stability, and of course, their historic name. When we talk about aromatic hydrocarbons, there is one molecule that is the superstar of the group, benzene. Benzene is the simplest aromatic hydrocarbon, and it's the blueprint for all the others. Its chemical formula is C6H6. That means it has 6 carbon atoms and 6 hydrogen atoms. The 6 carbon atoms form a perfect, flat, hexagonal ring, like a stop sign or a honeycomb cell. Each carbon atom in the ring is also bonded to one hydrogen atom. It's a beautifully simple and symmetrical molecule, and it's the foundation for this entire branch of chemistry. The structure of benzene was a huge puzzle for chemists for a very long time. They knew it had 6 carbons and 6 hydrogens, but they couldn't figure out how they were arranged to make a stable molecule. The secret, as we now know, is that special electron sharing. The 6 electrons are not in 3 separate double bonds, as you might draw on paper. Instead, they are shared equally among all 6 carbon atoms, forming a ring of electrons above and below the flat ring of atoms. This is what makes benzene so incredibly stable and gives it its unique properties. Think of it this way. If you had 3 separate double bonds, the molecule would be lopsided. Some bonds would be shorter and stronger than others. But in reality, all the carbon-carbon bonds in benzene are exactly the same length and strength. They are a perfect hybrid, somewhere between a single bond and a double bond. This perfect sharing is why scientists sometimes draw benzene as a hexagon with a circle in the middle. That circle represents the delocalized electrons, constantly moving and holding the whole molecule together in a state of perfect balance and stability. This stability is the most important feature of benzene and other aromatic compounds. It means that benzene doesn't react in the same way that other molecules with double bonds do. It's quite happy the way it is, and doesn't like to have its special ring broken. Instead of breaking the ring, it often undergoes reactions where one of its hydrogen atoms is replaced by something else, while the stable aromatic ring stays intact. This property makes benzene an incredibly useful building block for chemists to create a vast range of other useful substances. So why should we care about these stable rings of carbon and hydrogen? Because aromatic hydrocarbons are essential building blocks for countless things we use every single day. Their stability makes them a reliable starting point for making more complicated and useful molecules. Look around you. The world is full of products that started their life as a simple aromatic ring. From life-saving medicines to the clothes you wear, the influence of these compounds is absolutely massive. They are the unsung heroes of modern manufacturing and medicine. Let's start with plastics. Have you ever heard of polystyrene? It's used to make everything from disposable cups and foam packaging to the hard casing of your computer monitor. The styrene part of that name comes from an aromatic molecule. Chemists start with benzene, add a small group to it, and create styrene. Then, they link millions of these styrene molecules together to make the final plastic. Another important material, nylon, which is used in clothing, ropes, and carpets, also has aromatic compounds as part of its complex structure. Aromatic compounds are also critical in medicine. Many of the most important drugs we have contain an aromatic ring as part of their structure. Aspirin, one of the most common pain relievers in the world, is a great example. Its chemical structure is based on a benzene ring. That stable ring is the scaffold upon which the rest of the molecule is built. The same is true for many antibiotics, such as sulfanilamide, and even some vitamins. The unique shape and stability of the aromatic ring help these drug molecules fit perfectly into the right spots in our bodies to do their jobs. Understanding aromatic hydrocarbons is not just for scientists in a lab, it helps us understand the world we've built. It explains why certain materials are strong and durable, how some of our most effective medicines work, and even where some familiar smells come from. These molecules are a perfect example of how the arrangement of atoms determines its properties and its purpose. So next time you see a plastic container or take a pain reliever, you can think about the amazing science of the tiny, stable rings that made it all possible. Consider the world. It's full of science.